So we want to put all these ideas about Chatelier's principle, equilibrium shifts together, and talk about controlling equilibrium. So Le Chatelier's principle lets us predict how equilibrium will shift based on different perturbations, adding in reactants and products, changing the temperatures, decreasing the volume or increasing the volume, right? These sorts of variables that we have to control, to change to affect what is present at equilibrium. It lets us change, make more products, make fewer products, whatever we want to happen. So we have all of these kind of levers to change that let us control what the equilibrium looks like. And that's really, when we apply this to chemistry, it's because I generally want certain products, or I want certain substances, or don't. And I want to make sure I have the conditions set just so that I'm going to get more or less of whatever substance I want. Whether or not I'm calling it a reactant or product doesn't matter, but I want to be able to control which substances are present, either causing changes to occur or not occur, depending on my perspective. And if we look at an example, say N2 plus H2 gives me NH3. So this is taking nitrogen, reacting with hydrogen to make ammonia. This is a very, very common industrial process. And so I could think about different changes that I could make and what's going on. So what I'm looking at, this kind of graph is showing time on the horizontal axis and the relative concentrations. So we can see that initially they're all flat because I'm at equilibrium. So my amounts aren't changing. If I am trying to do chemistry, I generally want those concentrations to change. I want to make more product or whatever it is that I'm interested in. So I could do something like increase the concentration of one species. I could add more substances in this case, nitrogen. I'd see a jump in that concentration. So my actions in affecting the system take it out of equilibrium, and then all of the concentrations will change to get back to equilibrium and eventually get back to, again, another kind of flat concentration over time, which is a new equilibrium. I could then, because these are all gases, I could change the volumes. So I could change the volume or the pressure. In this case, I'm decreasing the volume. So the pressures all go up, the concentrations all go up. So again, I take the system out of equilibrium. The equilibrium constant isn't changing. What is changing is basically the kind of relative amounts of everything that I present. They're all crowded here, so that's why the pressure goes up. And again, it would proceed through, eventually the system goes back to equilibrium and we get another flattening out of my concentrations. Final thing I can do is change the temperature, where I can cause all sorts of things to change. I change the equilibrium constant, right? I change the value of Kc. That means a new equilibrium will be reached with new sort of relative amounts. But again, I will always go back to an equilibrium. So all of these places where I have the flat kind of concentrations is an equilibrium, and it's all the same reaction equilibrium, maybe a different constant if I change the temperature, but it's of the same equilibrium. But we can see the relative amounts of all of my substances are different at those different equilibriums. So if I want a particular substance, N2, H2, or NH3, whatever it is, I can make predictions as to what is present. So I can control what equilibrium looks like. Every single reaction will always go to equilibrium, but I have the ability as a chemist, to basically engineer my reaction to have that equilibrium look like what I want the most, what substances are present in the highest levels. So let's take a little more analytical approach to this. I'm doing this reaction, nitrogen plus hydrogen makes ammonia, and I want to maximize the concentration of NH3 at equilibrium. Okay, so I'm trying to make more product. So what I can do is add reactants. This comes from the idea of Le Chatelier's principle. We know if we want more product, add reactants, we'll shift more product, that would make more product. The thing is, this is probably what you're already doing kind of instinctively. If you want to make product, you add reactants to it. So we have that idea, but that's kind of the baseline idea of just like doing chemistry. Okay, so we need something more. Well, this reaction is a bunch of gas phase stuff. Everything here is a gas. So I can look and see that I want more product. The product side has 2 NH3. That's fewer gas molecules than the N2 and 3 H2 on the reactant side. So 4 to 2. So if I want to preference the side with fewer gas molecules, I can decrease the volume or increase the pressure. Either of those things would do it. Thing is, That's expensive. Increasing the pressure is functionally how this reaction is done, but that requires like special equipment. Your reaction mixture needs to be inside like a metal box that's strong enough to hold those pressures. So it is expensive to do that, run things at high pressure. We don't do that in the lab. Right? Everything's at standard pressure. So you can do it. That's what people do, but it is expensive. The other thing you can see, it's an exothermic reaction. So if you decrease the temperature, you would shift to the product side. We know that heat is on the product side. We can think about heat as a product because it's an exothermic reaction. Decreasing the temperature would lead to we're removing that heat, removing product. So we'd make more product, so more heat, and importantly, NH3 along with it. So the thing is, that would slow down your reaction, right? If you're decreasing the temperature, you would have more product at equilibrium, but it's going to take you longer to reach equilibrium. Okay, well, let's use a catalyst, right? That speeds it back up. The problem is the industrial catalyst that is used for this reaction only works at 400 degrees Celsius or higher. So this is kind of a bit of a problem. And you can see at the end of the day, reaction engineering is really hard. So what we want in this class to be able to know is how could we do all these things, right? How could we use adding reactants or products to shift it? How could we change the temperature? How could we change the volume? But actually engineering a reaction requires a ton of analysis and years of knowledge and a lot of kind of, because kinetics, oftentimes you got to decrease the temperature based on Le Chatelier's, but then that slows down the kinetics. And so you can see here, it is a lot of kind of difficult engineering, a lot of competing factors. With that in mind, participation 218, question 1. What effect would each of the following have on the equilibrium for the following exothermic reaction? C3H8 plus 5O2 yields 3CO2 and 4H2O. Everything's a gas. So 1, increasing the temperature, and 2, increasing the volume of the reaction container. This is the first question on participation 218, due Friday, February 18th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what effect would the following have on the equilibrium for this exothermic reaction? C3H8 gas plus 5O2 gas gives you 3CO2 gas and 4H2O gas. What would increasing the temperature do, and what would increasing the volume of the reaction container do? When we talk about controlling equilibrium, everything I've talked about so far and a lot of the ideas usually are concerned with making product, doing chemical synthesis. And that is true and very common. A lot of the times, that's exactly what we want, but not always. A lot of times, there are also many applications where we want a chemical equilibrium that can go back and forth. Either the reactants or the products could be there, and it could respond to stimulus. So this is how we do a lot of like chemical triggers. So things like any sort of testing that, when you have a different stimulus, so that could be light, that could be heat, that causes a shift in the equilibrium. Things like mood rings, if you think about you warm it up, it changes the temperature. That's equilibrium. You're shifting the reaction equilibrium. Things like explosive tests, where you swipe in the presence of that molecule, it causes an equilibrium shift. So different things like that, where you have these sorts of changes. An example would be something like transition lenses. Okay, and there the stimulus is light. So if you have no light, then you keep it clear, right? There's no external visible light, or usually it's ultraviolet light, that stimulates the reaction. So there's some sort of reactants, say, that could react, that are clear, and then once it gets exposed to UV light, it shifts the reaction to products. And then you have these dark colored product molecules. And then if you leave the ultraviolet light, it would go back to the uncolored, clear reactants. And so there's kind of this going back and forth. And the idea is the reaction can switch back and forth depending on the stimulus. Is the ultraviolet light there or not? Well, you're going to either have reactants or products. And there's going to be this kind of chemical switch, if you will, on off based on the stimulus. And so we use these a lot of times as a really powerful application of equilibrium, and specifically controlling equilibrium, that we can figure out and predict and engineer. And if you've ever used transition lenses, you know that a chemical switch only has so much life, so many times it can go through. Eventually, you just kind of end up looking like this all the time. That kind of mix between it, the kinetics eventually breaks down. The reaction gets kind of stuck. So at our first participation question, 218, this can be it for the Charlie's Principle. We've got one more kind of big ice table topic with the rest of these videos. See you there.